In this video, we take a look at finding the area of a triangle using determinants and the equation of lines and planes using determinants. So we continue with chapter 3.4 examples here. So in section 3.1, we saw that the signed area of a parallelogram is given by this 2 by 2 determinant x1, y1 in the first row, x2, y2 in the second row, taking that determinant where x1, y1, and x2, y2 correspond with the points kind of diagonally from each other, opposite the origin in this parallelogram. When we made our proof of this, we showed that you can think about chopping up a parallelogram, taking this triangle off and adding it to the other side, and our area just matches the area of a square or a rectangle. So we know when we're trying to find the area of a triangle, the area of a triangle is half the area of the corresponding rectangle. So we are going to show that the signed area of a triangle with vertices x1, y1, x2, y2, and x3, y3 is half times this determinant of x1, y1, 1 in the first row, x2, y2, 1 in the second row, and x3, y3, 1 in the second row. So make sure you see I multiply by half because we know the triangle corresponds with half the area of the rectangle. Okay, so we are going to take on our proof. So the first thing to think about is the area of a triangle is half the area of a parallelogram. And that makes sense because you could split your parallelogram up in half, or you could even think about rearranging your parallelogram to be a rectangle and know that the triangle is half the area of that rectangle. So the area of the triangle that we are going to figure out for these points, x1, y1, x2, y2, and x3, y3, is going to be half times the determinant for x2, y2, and x3, y3. Half times the determinant for x3, y3, and x1, y1, and half times the determinant for x1, y1, and x2, y2. If we think about what that expansion looks like, so imagine how we would expand this out. We would have 1/2 here times, let's see, x2, y3 minus x3, y2. And then we'd have plus x3, y1 minus x1, y3. And then we'd have plus x1, y2 minus x2, y1. And then that can get rearranged into this form, 1/2. And then we've got x1, y2 plus x2, y3. So I'm pulling the positive values out first here, plus x3, y1 minus x1, y3 minus x2, y1 minus x3, y2. So we see this corresponds with the determinant 1/2 multiplied by x1, y1 here in the top row with the 1 coefficient there, and then x2, y2 with the 1 coefficient in the third column, and then x3, y3 with the 1 coefficient in the third column. So thinking about the 1/2 out front, you can see as we go through cofactor expansion, we get exactly these results here. If you're taking this 1 here, then your corresponding cofactor matrix is going to be x2, y2 that corresponded with our first calculation over here, and so on for the other calculations. So for a triangle, we are going to say the signed area is A equals 1/2 this determinant. So we've got all the pairs of the points in the first 2 columns, and the third column is 1s. So note that if the vertices x1, y1, x2, y2, and x3, y3 are ordered clockwise, the area is positive, otherwise it's negative. And then your homework, you may run into a calculation where you have to ask for the absolute value of the area. So then you would just convert any negative areas to positive, because we don't like to think about conceptually negative areas maybe. Okay, so let's take a look at how we can apply this. So we are going to find the area of the triangle with these vertices at -1, 2, 2, 2, and -2, 4. So the first thing I'm going to do is set up my area calculation here. So my area is going to be 1/2 times the determinant where I put in my points x1, y1. So x1, y1 are -1 and 2, and then I'm going to put a 1 in the third column. And then I'm going to put an x2, y2, so that's 2, 2, and a 1 in the third column. And then -2, 4, and a 1 in the third column. So I'm going to head over to Simpy, and this could come out positive or negative, so we put a plus or minus out here in terms of the area. We're just going to think about the positive version because we are going to want to think about the area as positive or an absolute value. So I'm going to head over to Simpy and do the calculation for the determinant and see what our result works out to be. So I'll call my matrix A. And our first row is -1, 2, 1. Our second row is 2, 2, 1. And our third row is -2, 4, 1. Let's double check to make sure that matches. There it is, our points x, y in the first two columns, and our third column is all ones. And so we will just do det of A, all lowercase det. And our determinant works out to be 6. And of course, you could do it by hand going through the expansion that we just showed. And then verify it in Simpy if you like. So 1/2 times 6 is going to give us 3 for the area of that triangle. All right, and then of course the area of the triangle is 0 if and only if all 3 points are collinear, meaning they all lie on the same line. So you can verify points are collinear if and only if this determinant with the ones in the third column equals 0. All right. Similarly, we can find the equation of the line through these distinct points by setting this equal to 0, right? Because we know everything is on the same line if the determinant is 0, and then putting in variables x and y here to help us find the equation of the line and putting in the points that we know for x1, y1, and x2, y2. So let's look at some examples practicing that. So we are going to determine whether these points are collinear. So the points are 1, 2, 3, 4, and 5, 6. So let's go ahead and put them into our matrix here. Or we'll put it straight to the determinant. So we are going to put it into this determinant x1, y1, 1, x2, y2, 1, x3, y3, 1, and check to see, well, what is the value of that determinant? So our values are going to be 1, 2, 1, 3, 4, 1, 5, 6, 1. And you might be thinking, well, 1, 2, 3, 4, 5, 6. If you visualize that, that's probably on the same line if you think about the slope change there. Every time you increase x by 2, y is also increasing by 2. Let's head into Simpy to calculate the determinant of this matrix. Now I'm going to be lazy and I'm going to arrow up to when I created matrix A, and then just go ahead and replace the values in this matrix. So these points were 1, 2, and then of course a 1 in the third column, 3, 4, and then a 1 in the third column, and 5, 6, and then a 1 in the third column. So my new matrix A matches the matrix I've constructed to check if these points are collinear. And we do think visually these points are on the same line because the slope between them is the same. And so we get 0 as the determinant here. So that tells us these points are all on the same line or are collinear. So therefore, the points are collinear. Or in other words, on the same line. Okay, now let's rewrite our matrix we've been using to find the determinant with a x and a y in the first row, and then we could put in the values of x1, y1 in the second row with the 1 here, and the values x2, y2 in the second row with a 1 in the third column there. And use this to find the equation of a line. So if these are collinear, these should all equal 0. So we have x and y and a 1 here. We have -2 and 3 from the first point, and we put a 1 in the third spot. And then we have a -2 and a -4 from the second point with a 1 in the third spot. And then we want this to be collinear, so we have to set this equal to 0 here. So now we are going to use what we know about cofactor expansion to expand each of these, and we'll make use of the 1s over here. So this is going to expand. Let's see if I take the x as my starting multiple, and then the corresponding cofactor matrix is going to be the 3, -4, and 1, 1 if I go by the columns. And that x was in position 1, 1. So remember, -1 to the 1 plus 1 is going to be -1 squared, or just 1. Now we think about taking the y, and that y is in position row 1, column 2. So that is actually going to be a -1 to the third. So we're going to get a -1 here. So we're going to have minus y, and then the cofactor matrix that corresponds is going to be -2, 1 if I go by the rows, and -2, 1 in the next row. And then the 1 here, that'll give us our constant in the equation. That's going to be 1 times this cofactor matrix, -2, 3 by the rows, and -2, -4. Okay, so let's expand this out and see what it works out to be. So we're going to get 3 minus -4. So that's going to be 7x. And then we're going to get -2 minus -2, or -2 plus 2 here. So we're just going to have 0 y's. And we call it plus or minus 0 y, your choice. And then our constants here are going to be 8 minus -6. So we get plus 14 there. And this all equals 0. So this is basically 7x equals -14, or x equals -2. And that makes some sense, because if you look back at those points, oh yeah, both of those points, x is 2, so, or -2. So this must be a vertical line. So you can find vertical and horizontal lines through this process. Now, of course, it would probably be easier just to graph and see the line, but we want to see, if you're thinking about coding something, that this matrix determinant calculation is another valid way to find the equation of a line. So let's do the same calculation for the line passing through the points 0, 0, and 3, 4. So we are going to set up our determinant here. So we're going to have 0 equals x, y, 1, and then I'm going to put in our points 0, 0 with a 1 in the third column, and 3, 4 with a 1 in the third column. And then we can go ahead and start on our cofactor expansion. So we're going to have x multiplied by the determinant 0, 1, 4, 1. So see that I am just taking x here and using the cofactor when I take out row 1 and column 1. And then we know y is going to be a minus. So this will be minus the determinant of 0, 1 and 3, 1. And then we know z will be, or not z, 1, it'll be a plus 1 multiplied by 0, 0 and 3, 4 in our determinant. And then this is going to work out to be, let's see, for the x's, we have 1 minus 4. So, oh, sorry, 0 minus 4. 0 times 1 is 0, not 1. So 0 minus 4, so we get minus 4x. And remember, all of this is equal to 0 over here. And then for the y's, we get 0 minus 3, so minus negative 3y or plus 3y. And then for the constants, we get zeros because there's zeros in both those calculations. So our equation here is 0 equals negative 4x plus 3y, or you could say 0 equals 3y minus 4x. Or if you wanted to do it in terms of y, you could say 3y equals 4x. We know this point went through the origin, so we're not surprised that the constant part worked out to be 1, or you could say y equals, I'm sorry, the constant part worked out to be 0. So we have y equals 4/3 x. You can say plus 0 or just y equals 4/3 x. Okay, in the next video, we will look at some more applications to finding volume.